In the name of God, hello everyone. My name is Masoud. I'm a physics teacher. We are in Ferhua's website to explain the whole curriculum of physics. Also, we have an application. You can download it to follow our videos. Actually, in previous lesson, I solved the sample problem for you related to the gravitational force, related to the universal law of gravitational force. Today, I'm going to solve practice 1I, page 23. Let's say this practice includes two questions. Let's solve them together. Question number 1. If the mass of each ball in sample problem 1I is 0.8 kilogram. So go back to the sample problem. There are two, there were two, masses, two billiard balls. It says the mass of each ball is 0.8 kilogram. M1 and M2 is equal to 8 kilogram, 0.8 kilogram, or 0.8 kilogram, M1 and M2. At what distance between the balls will the gravitational force between the balls have the same magnitude as that in sample problem 1I? What does it mean? It means you bring the value of let's say gravitational force in sample problem 1I here, right? I wrote it here. I wrote it for you here. So M1 and M2 is given and it's 0.8 kilogram. And Fg is given. You can take it out from the sample problem, 8.92 times 10 to the power 11, let's say negative 11 Newton. Right. So what's unknown here? It says at what distance? You see, at what distance means R is unknown. R is unknown. We look for R. Just rearrange the equation. The equation of universal law of gravitation, Fg is equal to G capital M1, M2 divided by R squared. Rearrange it for R. So R is equal to radical, G capital M1, M2 goes up, and Fg, let's say, goes down under the radical. R is equal to square root of, G is constant. I told you you have to memorize it. 6.67 times 10 to the negative 11 multiplied by 0.8 multiplied by 0.8 divided by Fg. That's it. And I told you in previous lessons that whenever you observe the similar exponents or similar values, you can, let's say, simplify them to save your time, to make the calculation easy for you. That's why the answer R is equal to 0.7 meters. This question has another part. The second part, it says, how does the change in mass affect? How does the change in mass affect the magnitude of the gravitational force? What does it mean? Because in the previous problem, in sample problem, the mass of each object, the mass of the first object was 0.3, let's say, kilogram, right? And the mass of the second one was 0.4 kilogram. Cool? So here, mass of each object, let's say, increases. Mass of, if object increases, it says, what's the relationship, or how does the change in mass affect the gravitational force? Based on this equation, look here. Based on this equation, which kind of relationship is there between mass and gravitational force? Is it directly or inversely? For sure, you know the answer. It's directly because, let's say, Fg and M1 and M2 they are all in numerator. That's why we can say the more the mass is, the more the gravitational forces. Let me read the answer. The more the mass is, the more the gravitational force. This is the answer of second part. Or mathematically, I can say Fg is directly proportional to mass. Let's move on to question number to for this practice actually. Find the magnitude of the gravitational force a 67.5 kilogram person would experience while standing on the surface of Earth of the following planets. Right? Let's discuss them together. There's a person. The person stands on the surface of planet. For example, this is our globe, our planet. The person stands here above the surface of Earth, for example, right? The mass of a person is m small. The mass of planet is m capital. Or you can say m1, m2, no problem. It doesn't matter. So first of all, about the Earth actually, mass of Earth is given in the table. This is the planet. There are two planets, Earth and Mars, right? The first one, mass of Earth, planet Earth, 5.98 times 10 to the 24 kilogram. R is equal to 6.37 times 10 to the 6 meters, right? So we look for what? We look for Fg, because find the magnitude of gravitational force. We look for Fg, just let's say substitute the values. We don't have any conversion. It's very easy. G capital is constant. You see here in this solution, I brought the G into the numerator directly. And you can write the rule. You can change the rule. You can change the form of the rule like this. Fg is equal to G capital, M small, M capital, or M capital, M small divided by R squared. Yeah, you can, let's say, bring the G, let's say, to the numerator with M capital, M small. It doesn't matter. To avoid making a mistake. Fg is equal to 6.67. So this is the constant. Mass of a person, 67.5. Mass of Earth, right? This number divided by radius of Earth, 6.37 times 10 to the power 6 square. You have to square it actually. And the answer is 663.5 Newton. B, I'm gonna solve gravitational force of Mars on a person, or weight of a person on Mars. I want you to guess the result. And let me give you let's say an idea. Mars is smaller than our Earth. So how does the mass of the person, how does the weight of a person change over the Mars compared to the Earth? Does it increase or decrease? And actually, mass of planet determines the weight of an object, right? So B, Fg is equal to G capital M small M capital divided by R squared. G capital, this is the value of G. M small, mass of a person. M capital, mass of Mars, 6.34 times 10 to the power 23. You see it's smaller than Earth. It's so smaller than Earth actually. Divided by radius of Mars square. And the answer will be 242.6 Newton compared with the mass of the same person on the surface of Earth. You see that the Earth turns to the 1/3, right? 1/3 of the, let's say, of the mass, 1/3 of the weight of a person on Earth. So it reduces by a factor of 1/3 because planet is smaller, right? Thank you very much, guys, for watching this video. I hope you enjoyed this lecture, and bye for now.